Well, hello again. And we are continuing with calculus and the competition, which is worse, calculus or linear algebra. We're, in the race, each class both passes the other, right?
Calculus is worse.
Yeah.
I passed linear.
Yes. I hope it's a close race until the end.
I think you're biased, but I don't know.
Okay.
Yeah.
We have to move it. What's the plan?
So, this is the third class of fourth.
Or
Fourth?
we had one
Okay,
weekend
yeah,
Sunday.
So isn't it fifth? Well, no, today is Tuesday.
Yeah.
Okay. So it doesn't really matter. Okay, class number 4. Okay. So a recap. We learned the also beautiful definition of the limit of a sequence, which we wrote in the even more beautiful discrete mathematics form. For every epsilon, there exists a k such that for all n after k, the distance between the elements of the series and the limit is lesser than epsilon. I assume you didn't understand it fully yet. And I will say that it takes time, obviously, to understand it, but the way to understand it is not to give up, because what will happen, first of all, I will do a couple of examples which will prove the limit using the definition in easy cases. And that still won't be enough, but then we'll start to prove theorems using this definition. And if you try to understand each time, then eventually you will start to understand this idea. And it's also important, I spoke with Adi Bensby about it, because sometimes they skip fully understanding it in Calculus 1, and then Calculus 2 is horrible. So it's important to try to understand it, but if you keep trying, eventually it will become more and more clear. And with each proof and every example that we see, and the distinction between that and discrete mathematics is that within discrete mathematics, we didn't see any one definition that was so convoluted, but you switch up the definitions all the time. Every class in discrete mathematics, you learn a new definition. In calculus, this is one of the main one that will regurgitate over and over again. So that's the upside of calculus. Okay. And in linear algebra, I don't think we ever get to such things. Yeah, just matrices, simple matrices. No, there are hard things there, but not logically quantifier for everyone. There exists such a formal. Okay, so okay, class 2, class 4. We learned, is it narrow? Didn't narrow this. Oh, okay. We learned the definition of I assume the definition of a limit of a sequence And other than not understanding it at all, we also he's optimistic. We also learned. We also
Tried.
did not understand why do we need it. And one of the problems that the first few examples that are designed to help you to understand the definition throw you off from what do you need it for. And it makes students very anxious because I take something which is quite obvious and then I solve the problems using the very definition and say, oh, it's horrible, it's such a simple concept, why do you use definition to solve it? And the answer is, I don't use the definition to solve this simple example. I use this simple example to explain the definition. And I will show you what I mean. Example, say someone asks me, what is the limit of the sequence n plus 1 over n? What is the limit of the sequence? And I will show you now how you will answer such a question. Probably don't have such an easy question on the test, but suppose you have such a question on the test, how will I answer it on the test? I will do the following. Do you care to help me move along? How do I calculate this limit? What is the next step?
Well, it's just natural numbers, right?
Yes, it's a sequence, right? N is 1, 2, 3, and so forth.
Would you do when n is 1? Or would you just put it all the way to infinity?
You wish to put it all the way to infinity. That's the idea of limits, right? The question is, where does it tend to? But how can I calculate it?
Oh. Divided by n on top of the bottom.
Yeah, I split the fraction. That's the limit. It's not exactly what you said, but fine. Of 1 plus 1 over n. Do you agree on the first algebraic step? And then I look at this, 1 over n. What is its limit?
0.
0, right? Because n tends to infinity. So what will be the answer? 1. So that's the way. That is the way we calculate limits in this course. We will now prove that the limit is indeed 1 using the limit definition of the limit, I think. Definition of the limit, even though oh, it's 2 words. Even though it is completely unnecessary, just in order to understand the definition. Okay, do you see what I'm saying? Don't think that the purpose of the definition is to make things that are quite simple hard. It's not the purpose. In the test, I will not use the definition on such a sequence. Never, ever. Some lecturers, by the way, in order to make sure you understand the definition, they force your hand. They say, prove the limit using the definition. I hate such unnatural questions. If I want to make sure you understand the definition of a limit, I design a question which forces you to use it because there is no other way to solve it. I don't give you an answer that is possible to solve in one way, but you have to solve it in another horrible, stupid way. Okay? It's like in computer science when you tell you design your program, but don't use libraries. It doesn't, they do it a lot, right? Yeah. It doesn't teach you how to, there are enough problems which are hard enough that with all the libraries in the world, you'll still not be able to solve. These are the questions that you need to be asked, not try to do it yourself. I'm not completely dissing whatever computer science guys do, but but I do. Okay. Yeah, yeah. Yeah.
He's not doing.
No, but if you're not listening to me well, you don't want me because they ask you simple question and make sure you don't use the simple solution. I'll give you hard question where there is no simple solution. I'm not sure this is better.
If you're explaining it right, I don't care.
Yeah, no, I agree. Okay. Okay, so for the last time, my purpose is for you to be able to understand the definition of a limit for now. Okay, so we wish to prove that the limit of the sequence, the limit of the limit, that doesn't make sense. The limit of the sequence an equals n over 1 times n is 1. Okay, so before the actual proof, let's study this case. And you need to remember the main thing behind the definition, which is the concept of an area. We take an area of 1, and who remembers what do we expect to happen between the sequence and a certain area of 1?
That there's a finite amount of points outside the area.
Outside a finite amount of elements of the sequence, all of them are within the area. And it doesn't matter which area did I take. So what is the K in this definition? I said index last time, and some of you asked me afterwards that you don't know what an index is. It's the serial number of the element, right? The element could have a value of pi, but it is the 10th element of the sequence. So the index is 10. So K would be the number of elements outside of the area. This is the number of elements outside of the area. All the rest of the elements would be inside. If K is, I don't know, 100, then the number of the sequence with index 101, the serial number 101, the 101 element is within the area and all ones after it. Okay, and let's see it in the example below. So take any area of 1, consider an area of 1 of radius 1 over pi. It could be a radius, it's a number. So the area itself, what are the edges of said area from where to where?
You ask that again.
What is the segment? What is the segment? What is the left edge and the right edge?
The left edge is 1 minus.
1 minus 1 over pi
And 1 plus.
and 1 plus 1 over pi, right? Agreed? Let's draw it up using GeoGebra. So the distance will be 1 over pi. And the center will be 1. So the segment is from x equals L minus D to x equals L plus D. And let's color them the same color. It's purple this time. Stay with that. So these lines mark the area that we are currently looking at. It's not enough for the limit because the limit has to work for every area, large as small. But now we are looking at just one, just to understand what's happening here. So this is an area of 1. And now I'll ask you, when I draw the sequence, it will be on the x-axis. Where will the elements be? Are all of them going to be near 1 within the area? Not necessarily, right? Some of them could be outside of the area, but only a finite amount. Imagine there will be an infinite amount of elements of the sequence here. How can one say that the limit is 1 where infinite amount of elements are so far away from 1 that doesn't make sense? Okay, so let's do it. In a sequence, let's take the first 100, I don't know. Sequence of n over, no, it was n plus 1 over n, comma 0, where n goes from 1 to 100. Great. Okay, so you see there is a finite amount of elements outside of the area, and from a certain index forward, all of them are within. And I wish to study the index and actually find it. So A1, what is the first element of this sequence? What is A1?
2.
The number, the actual number, 2, right? Because when you plug in n equals 1, you get 1 plus 1 over 1, which is 2. So A1 is 2. Where is it? It's not a stew. A1 is 2. Where is it in the drawing? That in the illustration, that is A1, right? That is the first element of the sequence. Agreed? What is the second element of the sequence?
Like half.
3 halves, 1.5. This is the second element of the sequence. Agreed? I'm doing it slow, so if anyone have any question, please use it. It will go faster, quite fast. So A3, who is A3? That's 4/3, which is this point here. Is it within the area? No, but what happens afterwards? Everyone are within. So what is K here? It's 3, exactly. It's the index, not the value. It's the index of the element that afterwards everyone are here. Then after the kth element, where k equals 3, all elements of the sequence are within the given area that with radius epsilon, that's the name of the radii, equals 1 over pi. And what we need to prove we need to prove that such a function exists. To be clear, computer science function. I'm speaking about the programming languages. Such a function exists of the type. Which programming language did you learn so far? You have C? Okay, great. So int get k float epsilon. Okay, so there's supposed to be such a function that when given a radius epsilon, it is able to return an integer number which is k, such that after this index, all of the elements are within the bounds of the area for the given epsilon. And these are pairs. For every epsilon, there will be a k. For epsilon 1 over pi, the k was 3. But we need to prove that for every epsilon, there exists a pair. Why? Because for large epsilons, say these, I don't know, 2. If you take large enough radius, then all of the elements are within it. And I could take it behind, around, sorry, a different limit. Now I change the limit to 2 and the epsilon 2. So the area is between 0 and 4. All of the elements are here. Does that mean that 2 is the limit of the sequence? Why not? Because if I now take the radius to be a smaller number, what do you see here? This is something does not make sense.
It's in 1/2 instead of 2.
Wait. Ah, I did small l instead of large L. Okay, great. Okay, so there were a few problems before, but if I take an area of 2 of radius 1 over pi, what do I see? The first element is actually there. It's the dead center. It's 2. But what happens to the rest of the elements? They are all outside. I can't point out a certain index that afterwards all the elements are within the area because it's false, because 2 is actually not the limit of that sequence. But if I go again to L equals 1, and here it doesn't matter even if I take 1 over, I don't know, 50.
Yeah.
It's small.
Well, there-
However,
Infinite.
yeah, there exists such an element, such an index, that after this index, all of the elements are within. That's because 1 is actually the limit of the sequence. And I remind you that the fact that the sequence ends here is just because I drew up 100 elements. If I keep to 1,000 elements, you will see the points here. Let's do it for a second. 1,000 elements. Okay, and now you see it's much closer to 1, right? And okay, any questions so far? So I need to prove mathematically, just a second, that for every epsilon there exists such a k. And in general, this kind of algebra that if then inequalities is not taught in schools. And it's one of the problems. Usually when given an inequality in school, you solve wherever the inequality holds. But now the question is quite different. Is it true that this inequality holds after a certain case, after a certain amount of time has passed? That's the kind of question that we are not used to algebraically solve, and that adds to the confusion over the already convoluted definition. It's one of the problems. Yes, question? No, okay. Did I take any picture? Yeah, okay. Yeah.
Where do we use this K? Just to understand that there is a finite number of the dots outside the array.
Yeah, the
And-
K is the index, the last index that is outside, and the next indices should all, the elements should all be in.
Okay.
And now look at how it will look algebraically, right? Okay. So now for the actual solution. So the proof. So let there be light, yeah. Let there be no, we're in the Tohuvabohu part. Let there be let, let there be a positive epsilon given an arbitrary radius of an area. That's what I'm saying. Someone gave me an arbitrary radius. We must prove that there exists such an index K such that all elements of the sequence with indices larger than K, i.e. and larger than K, it is true that wait, just me. Let me just read the sentence. We must prove that there exists such an index K such that all elements of the sequence with indices larger than K are within the epsilon area of the limit L. That is more or less the the general form of any proof using the definition of a limit. Now we will adjust it to the exact example we are working with. So in this case, we need to find a K such that for all n larger than K, it is true that the distance between the element of the sequence in the nth place, the distance between this element and what? What do we measure the distance between an element of the sequence and the limit, the supposed limit, supposed, which and to prove we needed this distance to be lesser than epsilon. So this is the nth element. This is the nth element of the sequence.
The two lines that fit the distance.
Yes, that's absolute value. Yeah, the absolute value of the subtraction between two numbers is the distance between them. Agreed? Because if the left is bigger than the right, then it's just a subtraction, and if it's the other way around, that's why it's an absolute value. Do you agree so far? So now we have an algebraic problem. And like I said before, it's a bit awkward. We need to say that this inequality holds from a certain point onwards for every n that is larger than a given k. So let's work with let's develop or simplify that in equation. So what do we have here? First of all, lucky us, it's easy to see that n plus 1 over n is larger than 1. Then we can omit the absolute value. Do you agree? Usually it's not the case, by the way, but here it's quite easy. So n plus 1 over n minus 1 should be larger than epsilon, starting for a certain k.
Should be larger or smaller.
Smaller, so in other words, I said larger, you're right, but smaller. What will be the next algebraic step?
To simplify.
Yeah, what is the next simplification?
1 over
1 over n should be smaller than epsilon. Agreed? The next simplification, we usually try to single out the n, to extract n from the inequality. So n ought to be larger than 1 over epsilon. Does that make sense to you that n will be larger than 1 over epsilon? What happens if epsilon, the radius, is quite small? Say epsilon is 0.001. So what would n over epsilon be? 1,000.
Yeah.
Does it make sense that n would be larger than 1,000? Yes, because 1,000 is still a finite number. And after 1,000, all of the elements of the sequence will be within the bounds. And think about the 1 over epsilon we started with. The epsilon, the first epsilon I gave as an example was 1 over epsilon. So it was 1 over pi. What is 1 over epsilon if epsilon is 1 over pi?
Pi.
It's pi. What is the first natural number larger than pi? 4. Then the k is 3 because it works after it, right? That's how we saw the k being equal 3. Okay, so choose any k larger than 1 over epsilon. There exists such a k thanks to Archimedes. I think I said it once in the lectures that the fact that every real number has a natural number which is larger than it is called Archimedes' law, which is true. We just assume it. In a test, you don't have to write thanks to Archimedes. Just write, choose any k larger than 1 over epsilon. Okay, that's obviously there is such a number. Okay, and for all n larger than k, it is true that n is larger than k, obviously, which is larger than 1 over epsilon, and QED. So we found such an index that afterwards, all of the elements of the sequence are within the bounds, and that's exactly what we set out to do.
So we have just some harder example. And we can by this try to find epsilon or
We found not
Yeah,
epsilon.
yeah.
We don't find epsilon. Epsilon is an arbitrary radius.
Okay.
What we find is a formula, like the function I write here. Given an epsilon, you are supposed to return k.
Okay. Yeah.
That you are given the epsilon and you are returning the k.
Okay.
And the function here will be 1 over epsilon ceiling, right? You take 1 over epsilon, you round it up, that's the k you wish to have. Okay, and that's exactly. You can actually floor it, but if it's, yeah, I think you can actually floor it, but it doesn't matter. Another example. So prove that 1 over the square root. It's like 1 over ln of n. Where does it tend to, as in your intuition?
E.
Not at all.
Right.
N is a large number, right?
Zero.
It's 0. It's 1 over infinity. Okay. Now this would be interesting, and I'll show you why. So I'll take the GeoGebra, which I already prepared. The limit now will be 0. The distance, let's start with an easy one, 1. Okay. And the sequence, instead of n plus 1 over n, will be, let's write g of n equals ln of n. It will be g of n. Supposed to work. Okay. How many elements did I take? 1,000. That's interesting. Just looking here, not knowing anything else, where does it look like the right, sorry, no, I was mistaken. 1 over ln n, sorry. Okay, that makes much more sense. Okay, so it didn't just look like it, I was actually wrong. So here, what is the index that afterwards all of the elements are within the sequence?
Here 1.
1,
Yeah.
right? But okay, so now let's make it smaller, 1 over 10.
It looks like 1,000.
There are 1,000 elements, and we're not even close. Okay, that's why I like this. I usually do it with square roots, and it's easier to see in the eye. But with the ln, it's crazy. Let's take half. That's a bit easier. And when we'll solve it algebraically, you will see why it's so horrible. Half, okay, half is quite reasonable. Let's take 20. No, 20 is sorry, that's worse than a 10. I don't know, 1 over 7. 1 over 6. Okay, 1 over 6. Okay. So you see, when we take 1 over 6, we can still see with it, the k will be lesser than 1,000. That's the point. When we take the distance will be 1 over 7, the k is larger than 1,000. That's what we will see in a few minutes. Okay, so let's take 6, and let us screenshot. But I will add more elements. Let's take 10,000. Look, I added 10,000. It hardly budged. That's because lan is such. In Hebrew, we say lan is atzlan. Lan watzlan. It's lazy. I don't know if there is such a rhyme for English. Man is
Natural logarithm inflating.
yeah, lan is the natural logarithm. That's a great rhyme. No, like lan is at slam. That's what I meant. It's lazy. But that you don't have to. By the way, the first element is not even defined because you cannot divide by 0 and ln of 1 is 0. But it doesn't matter. The limit speaks about what will happen next, not what happened before. Okay, so that is what we need to prove by how do I call it? By experiment. By experiment, it seems that the K would be quite large. And now I noticed that I didn't. No, I think that's enough to see it here. You see many elements, and you see here the 0.2. I think it's enough. So now let's solve it algebraically and see why is it so large. So let there be epsilon. We need to choose a K such that for all n larger than K, what will be true?
The n is the absolute value of
The
a
distance between AN and what is the AN of this exercise? 1 over ln n. The distance between it and
0.
what is the limit? 0 should be smaller than epsilon. Agreed? That is the formula of the proof, written a bit more succinctly than before. But it's always this. Even in the theoretical uses of the theorems, in the proving of the theorems, it's just that here there will be I don't know, AN or AN plus BN or something general, not a specific example. Okay. So again, let us simplify. We simplify the inequality. And again, we omit ln of n is positive after 1. No, after 3 actually. So 1 of ln n should be smaller than epsilon. And I will write when assuming n is larger than 2. So ln of n. No, I was right. It's from no. From n equals 2. It's already positive. Sorry. Okay. So now we wish to extract n, to single out n. How can we do it? That's a bit of algebra. Who knows a bit of algebra? Or any algebra? That's nice.
E to the 1 over epsilon is less.
Yes, but that's where you did 2 steps. So the first step would be we wish 1 over epsilon to be smaller than ln of n.
Why not to do that?
Yes.
Because we're multiplying by ln of n, but ln of n
Yes.
could be 0.
No, it's positive. No, we ignore n equals 1. If ln of n is 0, then in any case it's false. Okay, we'll write assuming n is larger than 1. And what you have to remember, this idea we needed to work from a certain k forward. So I don't care if it doesn't work once or twice. Most part ln is positive and there's no problem. Okay, next, how do we extract n from this inequation? You take it to you put both sides to the power of e. Then e to the power of 1 over epsilon is supposed to be smaller than n. And does it make sense to you that n would be larger than e to the power of 1 over epsilon? The answer is yes, because this is a fixed constant number, and it doesn't matter how high, how large it is, still n would eventually pass it. And the e to the power of 1 over epsilon is completely missing the word, supported by our experiments. We saw that the k was quite large even for certain minimalistic epsilon, even 1 over 7. Why? Because if epsilon is 1 over 7, you get here e to the power of 7. That's a huge number. Look at it. E to the power of 7 by the experiments is definitely more than 1,000. Let's see. Wolfram e to the power of 7.
So look, so you zero in on the.
Yeah, you
on
see,
the
it's a wait, what is this? Where's the answer? Oh, it's here, yeah. Continued fraction. Who cares about continued fraction? In any case, you see it's about 1100, while e to the number of 6 is 400. That's why the k that would be larger than e to the power of 1 over 7 has to be more than 1,000, and that's what we saw in our experiments. Okay, so to finish the proof, we'll say choose any k larger than e to the power of 1 over epsilon. And indeed, for every n over k, it is true that n larger than k, larger than e to the power of 1 over epsilon, which is exactly what we needed for QET. Great. Notice in that example that if epsilon is 1 over 7, then k is larger than e to the power of 1 over of 7, which is larger than 1,000. And that is what we saw in our experiments above. Okay, so like I said, if it was an exam and someone will ask you what is the limit of 1 over ln n, all you would say is ln n tends to infinity, 1 over infinity is 0, and finish it. But I take these few easy examples because if we understand the example quite well, it helps us understand the definition of limit better. And that's what's important for me, more than all. Any questions so far? Yes,
Is 0 the left?
yes. That's the proof, right?
It just doesn't show on GeoGebra.
Ah, yeah, it does. Yeah, it doesn't show in GeoGebra because of the zoom in I made. If I zoom out enough, it does look like 0 is the limit. And the problem is that it's quite I don't know, זוחל. It's scrolling towards the limit because LAN is such what's LAN?
Can we do an example we disprove? Or we
Yes, that was about to be my next example. So I'll write what the following. Some students, you're some students. What is your name, by the way? Sam?
Sam.
Sammy. Sammy is some student. That's okay. Sammy student. Some students, not you personally, Sammy. Some students feel that with this process, we can prove that any number is the limit of any sequence. All we have to do is solve some inequality in equation. Okay, that's how it feels because I went to prove, I got an inequality, I solved the inequality, and that was the limit. So if I change the sequence, if I change the limit, I will get a different inequality, and then I will prove it, and everything will work fine. Obviously, this is not the case, but in order for you to be convinced that it's not the case, we need to see an example, and that's exactly what you asked for. And be careful what you wish for, Sammy. So let's try to prove. I'm not sure if the quotation mark is correct because we try to prove. So okay, I know what. Let's try to prove, okay, that 1 over square root of n tends to 1. We wish to prove that the limit of 1 over the square root of n is 1. That is absurd. It's obviously not the case. 1 over square root of 2 of n actually tends to 0. But we'll try to prove something false, and we're supposed to say that it won't be possible. Something would fail us. Agreed?
Something is like square root of 1 is 1 and 1 over 1 is 1.
So that is not the limit
Our
because
sequence
1 is a member of the sequence.
our sequence reached the limit.
So what? That's not a problem. I never said. I said the exact opposite. Like in the difference between maximum and supermode, reaching the limit is not a bad thing,
Yeah.
right? So that's by itself, it's not a problem. But it's definitely not a problem with the definition. We wish to study the definition, not just the intuitive ideas, right? So we're trying to prove, Thomas, we're trying to prove that 1 over square root of n tends to 1. It's not true. Okay, but we're trying to prove it nonetheless. So the exact same formulation. Given, instead of let, I say given. Given epsilon larger than 0, we need to find k such that for all n larger than k, it is true that, what do I need to write here?
K is larger than epsilon. What over epsilon?
No,
No.
Around
1 over
distance from 1
the
over.
distance between 1 over square root of n, the distance between the sequence elements of the sequence, and
One
one
is smaller than epsilon.
is smaller than epsilon. Read. So it's always the same formulation because that's the way discrete math works. The last part is always an inequality, which is the algebraic easy part. The part students have problems with is usually the quantifiers because they want this inequality to hold from a certain point forward. Okay, that's the change of thinking from high school that is needed here in order to algebraically solve such things. And by the way, we won't have a lot of exercises of this sense, but the quantifier will, that's the funny thing for me. The quantifiers will use a lot. Usually the algebraic thing here that you see in the start of the lectures and in the exercise maybe, this doesn't stay until the end. The main thing are the quantifiers, right? The algebraic stuff, you won't see as much. There will be some inequality, but it will be much simpler because you don't have a certain example. It will be general. You'll see that. In any case, simplify the inequation. So 1 over square root of n is always lesser or equal to 1. So this time we don't just omit the absolute value, but we actually reverse the subtraction. So this is the simplification, the first simplification of the inequality inequation. Do you agree so far?
Yeah.
Okay. Again, we wish to single n out, extract n. So 1 minus epsilon ought to be smaller than 1 over the square root of n. What will be the next step?
No.
Yeah, can would you multiply by square root of n and then do 1 over 1 minus epsilon?
Are we allowed to divide by 1 minus epsilon?
No,
It's-
because epsilon is smaller, like smaller
It
than one.
depends, but the answer actually depends, right? If 1 minus epsilon is smaller or equal to 0, the inequality is true or false, is always true. So that looks worse. We're trying to show that I can't just take a random sequence and a random number and show it's the limit, but it seems that it works so far, right? Let's see why is it true. Let's look at GeoGebra. So the limit again, no, it's not again. The limit now is 1, supposedly. The distance, what is the distance? 1 minus epsilon is negative. What does it mean? It tells us about epsilon.
Bigger than 1.
Bigger than 1. So let's say, or even 1. Let's take the epsilon to be 1. Okay? And the sequence is 1 over the square root of n. Is it true that the sequence is within these bounds?
Yeah.
Yes. But why are they within the bounds? Not because we have the right limit. It's because we took a large area. That works since when epsilon is larger or equal to 1, the area around 1 is large enough to contain the entirety of the sequence. Luckily, whoever thought about definition of a limit, envision this case.
But here,
That is why, and what did we demand? That's why we demand. What do we demand in order to solve this problem? That it will work not only for epsilon larger than 1, but
All epsilon.
for all epsilon, for all values of epsilon. It's not enough for it to work than larger than or 1. It's not enough for it to work for larger than 1/1,000,000. You need it to work for every possible positive distance, as large as small, as well as large as well. You understood me. Okay. So now, if epsilon is smaller than 1, then 1 minus epsilon is positive, and we can safely divide. Be careful what you wish for, because now it won't work, but now the simplification is allowed. So I'm turning back. I'm going back to the point where we stopped. I'm going back to the point where we stopped, and I say, okay, so we need a square root of n to be larger than 1/1 minus epsilon. Because both sides are positive, we can square them, and larger now, but I mean, that is quite important, smaller, right? Because when I multiply it by square root of n, it goes to the left side, which is the smaller side. So we need that n would be smaller than 1/1 minus epsilon squared. Is it true? Is it true that for all n apart from a finite amount, the equation above holds from a certain k onwards? No. It's quite the opposite. From a certain k, it does not hold. For all n larger than 1/1 minus epsilon squared, or equally then, it does not. So it's the opposite. From a certain point forward, all of the elements are not within the area. And let's take an example. Take the area over sides 1/10. Okay, you see? No, it's too soon. 1/, I don't know, 1/2. Okay, or even 3/4. Great. Okay, so if I take this epsilon, I see that from a certain point forward, all of the elements are outside of the area. Not of course, not within the area, because that is not the limit. They go to the limit, the actual limit, which is near zero, which is far away from one. What does it mean far away? Some positive distance is far away enough. Okay? And yes, questions so far. Yes, thoughts.
Can you go back to the calculation part?
The,
Here, yeah. So like, where in the math do you see that this is false, or do you need
because you see the natural numbers should be, the index should be less than a finite number. How many natural numbers are smaller than 1,000? 1,000, that's what I'm saying. You see?
okay.
All of the numbers that are bigger than these numbers are outside. The amount of numbers which are smaller than this number is a finite amount. The very number, the ceiling of this number, or the floor, whatever, something. Okay? Any questions up until now?
Can you
Yes.
just scroll up a bit? A little bit down.
Yes.
No, it's-
Just to do like this? Okay, yes.
no,
Here.
just a little bit up.
Oh.
A little bit up, just the top of the calculation. Okay, yeah. Where? I'm confused. Where did we get the topic from? It was originally it was one over root n.
We stopped here, and then we say we wish to extract n. But then we said we are not sure if 1 minus epsilon is positive or negative and how to algebraically work with it. And that's what we did, what we usually do. We divided the word into two cases. Either 1 minus epsilon is positive or negative. If it's negative, I said this, then it works always. So k could be 1. From the very first element, the sequence is within the area. And then I showed you in GeoGebra why does it make sense? Because if epsilon is larger than 1, then the area would be from 1 minus epsilon, which includes 0.
Right.
So all of the sequence is there. And then I say, and what happens if epsilon is if 1 minus epsilon is not negative? If it's positive, it's also an option. And then we continued to prove and simplify the equation in this case. And then we found out that our demands are impossible. We wish to prove that this inequality holds from a certain point onwards. It doesn't. It's the exact opposite. From a certain point onwards, it doesn't hold. Any questions so far? So far, up until now, we discussed finite limits. What would you say about the limit of, I don't know, the sequence n squared? What would you say the limit of the sequence n squared is? Infinity, obviously. Agreed? That is not covered by our insurance. That is not covered by our definition, because our definition assumed a real number and the area of the real number. What will be the so-called area of infinity? So infinity? From where to where? Infinity. That's not good enough. Why? Because I wish to say that the elements of the sequence are in the area of the limit. So they are not infinity. They are never infinity, right? So infinity. So no. Infinity. Oh wow. I lost a lot of letters there. Okay, infinity. So what would be the area of infinity? And before I'll tell you the answer, I wish you to start to think about it for yourself. Why would you say n squared tends to infinity? If you wish to convince a layman person that n squareds tend to infinity, what would you tell them? Why is this sequence close to infinity?
Because it's natural.
That doesn't.
Whichever.
And maybe it will help that I will write instead of n squared. It seems too obvious. Now it's much less obvious, right? Why does ln of n tends to infinity? Now you're not even sure it's true. Okay. So now you have to work a bit hard. If yes,
Because for every because n comes from the natural numbers and the natural numbers is an infinite set. It means for every n we have, there's an n that's bigger. And
not true. That
What?
it is true that every natural number has a bigger one, but the fact that every number has a bigger one does not mean tends to infinity, right? The series 0.9, 0.99, 0.999 is ever increasing, and it doesn't tend to infinity.
I mean,
It's actually a subject of the course, increasing and decreasing sequences. So no, that's not
I
the
mean-
answer.
what was easy in n squared and isn't easy in logarithms is
I
that,
try to help you give me an answer rather than it's obvious.
yeah,
right?
no. Because for n squared, for every n, the distance between each one was bigger. So here it's not.
Okay, great. So I did my job. So I take down that horrible answer you wanted to give us.
Which
No,
works.
it's true in a way. It's more like series because what you say now, it's series is the infinite sum. So you when you look at the distance between each two elements, the series is the sum of distances. So you made it into a series, but that's the next subject. Let's stick with sequences. It's hard enough. Why is ln of n equals to infinity? What would you expect from a series, a sequence that tends to infinity to hold? Give me one fact about a sequence that tends to infinity that we can make sure that it happens here. If someone gave me a random sequence and told me this tends to infinity, what do I expect to find, for instance, within that sequence?
That there exists no L such that for all epsilon that number.
That's true, but that's not enough. That's what you say, it's that it doesn't tend to a finite number. But what makes it do tend positively to infinity? Where should the numbers be?
Oh.
Yes.
that with inside that for any for any L there exists a K that for any n bigger than the K all of the points are outside of the area. Most of the points are outside the area and a finite amount are inside.
You are completely correct.
Incorrect.
No, correct.
Ah,
Correct. Completely correct. Say 1,000,000. Is it true that ln of n will sometime be larger than 1,000,000? At which number? E to the power of million,
Yeah.
right? E to the power of million. So it's a huge, enormous number, but it does happen. And what will happen after it passes 1,000,000? It will stay there. So the area of infinity is from a certain point outward. that would be the area of infinity. It doesn't matter which number I'll take on the real line. All of the series should, from some point forward, be to the right of that given point. So I'll write it. So what will be the so-called area of infinity? It will be the half line. In Hebrew, we call it keren. I'm not sure how do we call it in English. A line that starts, it's half a line. It starts with one point.
Right.
Ray, yes, keren.
Yeah.
So it's the same word. Okay. Array of from some number forward. That is the area of infinity. Array. Okay, rather than a segment. It's actually what you said.
Array.
Ray. It's called array.
So we just
Array.
took
Like
the
an array isn't like
Right.
like array.
No array, not array. Computer science post from my
It's
side.
a array.
Array.
Sorry.
Array.
And we took the core biggest number we can took some
Yeah.
number of where
Yeah.
and we say like there is some points out right on the right.
There is only a finite number of points of the sequence outside of the array.
Uh-huh.
Most of them are within. And I will write the definition now. Yes.
Can't we generalize this and say the other way around, it's also right, but
Yeah, from negative infinity, yes.
no, not negative infinity, but when it tends to, for example, to zero. Okay, can you show the picture where we got to zero?
Yeah.
So can't we technically say that we have array here, and then on one side, it's also a finite number.
But it's not true that all of the numbers are within the array, right? If you take the array from here onwards, all of the elements are here. They are outside of the array.
we take it that way.
So if you take it that way, and what happens if you take the array that starts here?
We just don't.
So you know, but you need to
No, but
take.
why-
It doesn't work for every array. That's
But what I'm
always
saying,
the thing.
why do we need to take two borders where we can take only the rightmost?
It's not enough. That's what I'm saying. Because if you don't take two borders, you just take one of them. And what is that? You need two borders, right? If you just take one, so I say put this line somewhere here, and everyone are out, right?
Well, we don't put it here because we're putting it around this point.
So you want so you want a one-sided border.
Yeah,
One-sided
basically
border
array.
would work.
which is basically array, no?
It's not array, first of all, no. Array, that's half a segment. It's not array. Array is infinite, so that's one thing. But if I'll take half an area, that's I could do it, but then I lose some of the sequences. All the sequences that tends to zero from the left, you would lose. All the sequences that goes left, right, you would lose. So that's not
Oh, well,
not a good definition. But in any case, it's not an array,
Okay.
right? And for infinity, it doesn't happen because a sequence can go to infinity, pass it on the right, and then go back because you cannot pass infinity. With real numbers, you can. The sequence can pass the limit, then go back and forth and back and forth. And that's one of the reasons why the definition was so convoluted. If the series was, the sequence was strictly decreasing or increasing, then like we said, we could have used supremum or infimum just as well for a limit. But we wish to accommodate the idea that it moves around, and in infinity, it's one-sided because you cannot pass it to the other side.
Again,
Yes.
so array is just everything from a point to
Yeah, what I wrote here, from M to infinity. And you will see the definition in a bit, right now. So, definition. AN, the sequence AN tends to infinity if for all M, I usually like positive M's even though we don't have to. There exists K, natural K. Nope. natural K such that for all n larger than K, it is true that, who can finish my sentence? So up till now we say for all m there exists an index that after this index, what happens to the sequence? Where do you expect to find the elements of the sequence? And tell me that algebraically, not with the Queen of England wave. So what is the inequality that I write here? Yes. Yes. Am is bigger than m. That's all. That's within the ray. That's exactly what Sammy said, right? It's outside of the area, so there was no actual area here, but to the right of the how do I say, the arbitrary point on the straight line, it's it's right. Agreed?
Yeah, that makes sense because so if a function doesn't have a limit, it's a line. If it tends to infinity, it's a ray. And if it tends to a constant, then it's a segment. Essentially.
I'm not sure. I'm not
Many
sure
words.
what you said. I'm not sure what I think you said has anything to do with this. I, no, you're obsessed with the concept of ray. I don't think it really matters.
I'm trying to like just generalize it in my head, and because what we did with the board is essentially we defined a segment, not a ray.
Yeah.
So it's
An area. I like it to think of it as an area of the limit. And when the limit is a finite number, an area will be a segment. And when the limit is infinite, the area would be a ray. And what you asked before about the two sides, that's something different. And for me, when I said this the sequence 10 to 3, I don't wish to say that it's necessarily more than 3 or less than 3. And that's why I take the two-side area. In function, we will see it. Because in function, sometimes I do wish to look at the one-sided limit. What happens to the right, what happens to the left, and then we'll have one-sided areas. Okay? And any questions so far? So I'm almost finished for today. I'll give you an exercise to think about for next lesson, and I will prove it. So theorem, if an tends to infinity, then 1 over an tends to 0. Prove that for next lesson. Both of them are using the one of them is the definition which is given. We know that an tends to infinity, and one of them is the definition we need to prove that 1 over an goes to 0. That is the first theorem that we will prove using the definitions, and we are not able to do it without the definition. Just intuitively, we could say, yeah, that makes sense. But in order to actually do a mathematical proof, we have to have mathematical definitions. So that's what we need the definitions for, to prove general theorems like that. And then we use these general theorems in order to calculate limits, like here. Like saying, okay, because ln of n tends to infinity, 1 over it tends to 0, and finish the question like that. Okay? So goodbye, have a nice weekend. Not now, but I won't see you until the weekend.
In the future.
Yes.